perfectly. Thank you. So thank you so much for coming to day 2 of the PUNCH6 meeting. We're really excited to move on with this meeting. So let's do it. So the first session, we're going to have a talk. Originally was Anna Malinishenko, who was not able to be here. But we are going to have a wonderful tag team of Elena Provornikova and Dave Webb to provide that information. Elena, do you want to come up? Take it away.
Right. Thank you, Sarah, and good morning, everybody. So I will just spend a few minutes to talk about the CME challenge on behalf of Annie. So CME challenge is the data set that we created, open to the Punch team, open to the community. So this data set contains the simulated Punch observations of different CMEs that emerge and evolve in the realistic solar wind. So to create this set of synthetic observations, we ran a few simulations with the global MHD model of the inner helisphere with the CME. So this is the kind of the schematic of our model. So the resulting simulation of the Gamma helium model with the CME, you can see on the right side. So we are this model describes the global solar wind structure, which is driven by observed solar magnetograms. And the CME itself is modeled over the Gibson-Low MHD model, which has internal magnetic field. So this is just an example of the CME. And we ran a few simulations, 4 to be exact, with the Gamma model using the same solar wind background. So it's a steady state solar wind background, and setting different parameters for the CME. And we then generated, using the density distribution from the 3D density distribution from the Gamma simulation, we then ran calculations of the total brightness and polarized brightness in the punch field of view and projection. So Annie did all this work. And so those 4 CME events, so the first CME, which we call CME 0, so that's the reference case, and we reveal all the properties of the CME in the simulation. So we let community know what that CME was exactly. And so the idea is that folks who do reconstruction of the 3-dimensional distribution of density in the inner helisphere can run their reconstruction techniques on that CME 0 case and compare the output with the simulation density, because we call it as a ground truth, because you ran the simulation, you know about the density distribution 3D in time. So for the CME 0 case, we reveal all the properties, all the parameters we set in the simulation. So this is the case for the reconstruction and validation of the methods. But then, yeah.
I didn't share screen. Hold on. Sorry, that's my fault. Keep going. Keep talking.
Yeah. So for the CME 1 to 3, so those simulations, we give the synthetic images we created, but we do not tell you what CMEs we put in the simulation. So that's the challenge, to reconstruct the CME structure and then compare with the simulations. And so this is the CME 0 simulation and synthetic observations. So you see the total brightness and polarized brightness images for one particular time. And so these are the snapshot from the website that Annie created, and she made it available to the community. And those tables contain the parameters of that CME that we assumed in this case, and also the database of all the images to use for the reconstruction methods. And then this is another example, CME 2. So this is, you can see This is the CME here, the tiny CME going kind of toward the south. And in this case, we don't tell you what the CME2 was, what the properties, what the width, and what the magnetic field strength and all the other parameters. And there is a database of images that can be used for the reconstruction. So this is a quick summary about the CME challenge, and now I think I can transition to Dave, who will talk about the using reconstruction techniques.
Okay. Hi, it's not full screen here?
Look up there.
I can't see that. Okay, Annie and I are co-leaders of Punch Working Group 2A, and my part of this is emphasizing the work that people have done on CME tracking and space weather forecasting building up to Punch. And this is a group of 6 people or groups whom I'm going to quickly review. How do I move? Okay.
Doing just the arrow. Yeah.
Okay.
Down arrow.
All right. So, and just say you can read this. The advantages of Punch for tracking and resolving CMEs is basically that the high resolution allows us to see the substructure much better of CMEs and hopefully shocks. And the PB data will give us, the polarization data will give us much better tracking information on CMEs. Now, the first one is Hugh Morgan and his group have this ACME 3D detection and tracking program, which is operating in real time for use at the UK Met Office. It's a modular software package designed to accommodate new data sets such as Punch. Punch will improve, as we know, the quality of space weather forecasting because of its high quality imaging and routine, frequent data capture, and its PB images will allow collecting characteristics, especially on the tracking, which of course will be useful, very useful for forecasting because you need to know where the particular structures are headed with respect to an object like Earth. And these just show 2 examples quickly. You probably can't see them very well. The left is a synoptic chart showing how they fit the CME with the cone model and so forth. And through their process, they can see over there on the left, you see the X cross, which marks the location of where they think the CME is coming from. The Earth is in the center of that map. And below are near real-time images which show the fitting of the CME front and the cone model in green and red, if you can see them, green and yellow points. Okay. Make sure that's, okay, this is the using Punch for real-time data, CME data arrival predictions. Chris Mostel and his group at Gratz are using their drag-based, they call it the ellipse evolution model based on heliospheric imager observations. They've been primarily using it lately with stereo data. The Punch observations can be incorporated easily into their model to look at the interplanetary evolution of CMEs to predict their arrival time, speed, and likelihood of arrival at Earth. The model was developed and tested to serve as a fast and easy way to apply CME propagation models that only needs the time elongation measurements to the front as observed in HI images. And of course, Punch is very relevant to this. And on the left, there's a series of showing the stereo beacon data, the quick look space weather data from stereo helio HIA instrument. On the left is the actual data, in the middle is where how they enhance it with their procedures to look for the fronts. And on the right side is the science data itself. So you can see their enhanced beacon data is pretty close to what they get from the much later arriving science data. And on the right, it shows their plot of the CME coming out in the HI field of view with various fronts that their generative model finds for tracking. I also mentioned, I think it's important, the Gratz Group have a catalog of in situ observations of CMEs containing magnetic obstacles like flex ropes. And PUNCH will be added to their catalog, so that I think is a big advantage right away. This catalog, I think, can you hear me all right? Yes. The catalog, I think, is the events are entered fairly routinely and pretty rapidly. And it contains ICMEs detected with active spacecraft, and there's a list there. And the arrival times are of different spacecraft can be validated by using this set of data together on one event. Okay. Then Arno Theresian and NRL has their forward modeling techniques, which are going to apply to PUNCH by following the CME fronts out through the NIFI into the WIFI field of view. They have the graduated cylindrical shell model, 3D geometrical model of the flex rope CME. Its purpose is to fit the CME direction, extent, and speed. We've seen examples of this already at the meeting. They're updating this forward modeling tool to use with the PUNCH data and the combined mosaic. And they will add settings for the PUNCH instruments based on the world coordinate system, which we talked about earlier, and the FITS header pointing data, optical projection, and distortion. The tool will allow using data not only from PUNCH and the older LASCO and SECI instruments, but also can be fit simultaneously data from WSPR, Solar High HIs, and the new C-Core chronographs. Volker and his Solar Heliospheric and Space Weather Research Group at Göttingen in Germany wants to use the data from PUNCH to reconstruct global 3D structure of CMEs and associated shock waves and track their evolution. The goal is primarily to understand the kinematics of CME propagation and facilitate more precise space weather forecasts by using the derived parameters in the group's existing CME dynamic drag and drag propagation models. And they're, of course, involved with the European Vigil mission, which would be at L5. And it'll be, they'll apply this work to that planning. Okay, moving on. Now, PUNCH tomographic reconstruction, Bernie Jackson stuff, I'll emphasize right now. He has a poster right out front. And so if I can't get through all this, you can talk to him and look at the poster. So UCSD has an iterative time-dependent 3D reconstruction program, which works throughout the inner heliosphere based on using IPS and Thompson scattering brightness observation, IPS primarily for velocities. It's this data he's been testing it with a SME brightness to learn how well the 3D reconstruction is performed to reproduce a known CME in the background solar wind. Let's see, he generates density volumes. Let's see, these images show at the top are fisheye views with the sun at the center. And at the bottom are ecliptic views in the ecliptic plane of the density structures that are reconstructed using his program. And a heliospheric density fall off of R squared is involved in these so that you can better see the structures as they evolve out to 1 AU. So these, I'm going to save the details for looking at the poster, talking to Bernie. But in using the SME data, he's trying to reconstruct what we might be able to how it might work with PUNCH data. What SME did not have polarized brightness data, PUNCH will. So here he's trying to recreate what the pseudo brightness and pseudo PB data might look, and then the ratio. So the ratio PB over B is in the lower right hand image there. Bernie uses ground truth for determining how accurate these densities are by using the Thompson scattering results, how well the Thompson scattering reconstructed results of density agree with spacecraft monitors at the same time, especially at 1 AU like wind. And usually the correlation is very good. Again, he has plots of this on his poster. Up to date, he's been using rather crude resolution of 5-degree centers. Recent analysis, he's been able to boost this to 1-degree image, so higher resolution, which will be used with PUNCH. The key problem or question is how well we can determine flow speeds in the heliosphere. And we've talked about the two methods being used right now in the correlation tracking for SOC pipeline and the ball tracking method that has been talked about. Okay, I'm going to try to quickly get through Enlil is Ducham's model. We all know about this. It's been used a lot for simulating the propagation of CMEs in the heliosphere. It's a 3D numerical model used extensively in space weather operations. It's available through the CCMC and is used operationally by NOAA, NASA, the UK Met Office, and in Korea and Australia. It uses an ideal 3D MHD model to characterize the fully ionized plasma with volumetric heating. And I'm not going to be able to go through all this. This is an example of one event that he shows where in that color picture, you can see the CME itself is outlined in the black, and this is superimposed on the solar wind background. And below, on the bottom of this is the observed solar wind velocity at Earth. In the solid, the dotted blue is the background, the actual wind, and the other plots show the results from this model at 1 AU. And this is the simulated data. On the left is the ecliptic plane view of the CME. In the middle is the view from Earth, as reconstructed as we might see it from PUNCH, for instance. And PUNCH will give us an advantage of, let's see, current white light imaging, including HIs, have limitations. But of course, PUNCH will give us much better quality heliospheric images, including polarized brightness, to enhance our understanding of CMEs and improve our forecasting capabilities. Thank you.
Thank you, Dave. And as yesterday, we're going to be doing our Q&A at the end of the session. Before we move on to the next speaker, I just wanted to call your attention to a couple links that have appeared in the chat. So the first one is quite useful because it is a launch schedule, which explicitly says that the launch date is now, where is it? The 2nd of March at 7:09 p.m. So it is, in fact, official. But for those of you in the room who want to find this, I was able to do it by going to rocketlaunch.org and navigate pretty well scheduled launches, Vandenberg Air Force Base. And this was a nice way to find out the latest official launch date. So right now it is Sunday at 7:09 p.m. I also want to point out a couple links that I put in the chat. And I mentioned the other day that we have topical focus groups as a way to really extend out to the community. The flow tracking group, which is what Raphael presented yesterday, and then the ICME challenge focus group. And what Elena showed you today is all on this link. So you should be able to find it pretty easily by going to the PUNCH website. Okay, let me go on to the next talk, which is Kurt de Koning. And Kurt is going to be talking about polarization. I'll find you. Oh, you're right here. All right, go ahead, Kurt.
All right, good morning. Yes, I'm going to be talking about polarization. CIRs does appear in the title, but most of the talk will actually be about the polarization ratio. So what is the polarization ratio? Well, the polarization ratio, PR, is, in fact, as the name suggests, is a ratio between different polarization states. So it's a ratio between radial brightness and tangential brightness. And I did notice that when the PUNCH level 2 data comes out, it will actually consist of these two images, the BR and the BT, so that we could right away start making polarization ratio images from level 2 data. We can also combine the BR and BT into total brightness TB and partial polarized brightness, excuse me, PB. And then by taking this ratio of the difference of these two brightnesses over the sum of the two brightnesses is another way of calculating the polarization ratio. So what we now need to go and do is, if we stick the expressions, the appropriate expressions for the polarized or for the brightness into these ratio expressions, what we end up with is this integral expression, one integral divided by another integral, which isn't very informative, really. So just to get a better idea of what's going on here, if you're really interested, if you want to do a deep dive into where that expression comes from, and you want to do a deep dive into Thomson scattering of white light off of electrons in a solar corona, these first three papers, the ones by Billings, Howard and Tappan and Inhester, is the place to go and look. If you want to do a shallow dive, looking at how the polarization ratio extends from these more fundamental analysis, then you can look at this paper by de Koning et al., which is supposed to have been out by the time the launch happens. But just like the launch of PUNCH, this paper has also been delayed, although it has been delayed by more than a few days. So there's that problem. Yeah, but one of these days that paper will actually come out, and you'll be able to read all about it if you're interested. So one of the key steps in deriving that expression, the polarization ratio expression from a few slides back, is that what we employ is the small sun approximation. And basically what the small sun approximation does is it says that the location at which the Thomson scattering occurs within the solar corona, so the location R, the radial distance R, should be much larger than the radius of the sun, R solar. Practically, what this means is, and I'm defining practically kind of quantitatively, looking at comparing the exact expression to the approximate expression, and I'm looking for the place where the approximation introduces less than 1% error. And this seems to occur at around about the point where the radial distance at which scattering occurs is greater than 9 R solar, or where the viewing angle epsilon is greater than 2.5 degrees. So this means that the approximation that I'm going to be discussing is definitely valid everywhere within the WIFI field of view, and is in fact valid in most of the NIFI field of view. So what we're going to discuss here should apply to the better part of all the images, the mosaic images that we will be seeing. Then to get a better idea of what is, again, a little bit of better idea of what's going on within the polarization integrals that I showed, we have this diagram here. The sun is this star over here. The observer is this green cross over here. The circle that goes all the way around, that's the Thomson sphere. And then the polarization integrals are happening along this blue line, the line of sight, which extends from the observer out across the Thomson sphere and all the way out to infinity. Now we can, what the polarization ratio, what the polarization integrals do, the brightness integrals do, I shouldn't be calling them polarization integrals, they're Thomson scattering integrals. So what the brightness integrals do is that they sum up contributions of Thomson scattered white light from every location, every location with electron density anywhere along this line of sight. So that's what the integral is doing. It's covering, taking contributions from every location along the line of sight and adding it together. That's the signal that we're measuring. Now, there's two ways to measure or position along the line of sight. We can measure position along the line of sight either looking at increments of normal equal increments of position, so looking at it in standard position coordinates, or we can look at it in equal increments of angle. Now, I'm going to be expressing it, or as you may have remembered from a couple of slides ago over here, we're doing it in equal increments of angle. And the reason is because when we use this angle, which is this angle here, this big angle here, measured with respect to this dotted brown line. And the dotted brown line is simply a line that is parallel to the line of sight, but it is centered on or it extends through the sun, location of the sun. When we put our integral in the terms of this angle, then the integrals happen to come down to a very nice, simple, compact form, a very pleasing compact form. So it's just nice to have that. So what we're looking for now then is, again, I said that you could express position along the line of sight either in terms of regular position, linear position L, or in terms of angular position psi. So here we have a plot that shows how the linear position varies with respect to the angular position. With respect to linear position, the integral is going, like I said, from the observer's location at 0 all the way out to infinity. We're not seeing that on here because we've got a logarithmic scale. In terms of angular position, the location is going from the observer at the angle epsilon all the way out to 180 degrees. So 180 degrees in angular position is equal to infinity in linear position. Also, in terms of regular position, the Thomson sphere is this dotted line over here, and it varies depending on what your line of sight is. In terms of angular position, the Thomson sphere is this dotted line over here, and it is always at 90 degrees. So that's just a quick overview of how the two positions vary. So now what we're interested in, here we have this expression again, and what we're interested in is what is the density along the line of sight. So we need to find an expression or choose an expression for what the density along the line of sight is. So here we have, finally, we have a CIR that it's not just in the title, but it actually has a whole slide dedicated to it. Here we have a picture of a CIR, position of the sun here again as this star, right here. And here is the position of the observer as a dot. We again have the Thomson sphere as this circle. And then we have the fast solar wind emanating from a coronal hole on the sun. And the fast solar wind is showing up on as these red lines. Then the fast solar wind is plowing into the slow solar wind ahead of the fast solar wind. And it is creating this compression region, which is this blue region in front of the red. And then also, as the fast solar wind transitions back to the slow solar wind, we have a rarefaction region that is occurring behind the fast solar wind in this green line over here. So here's your basic anatomy of CIR. Now, what we're interested in is looking at how what is the density density expression. So if you look at a typical solar wind density, what we always assume is that because the solar wind is radially expanding, is that the density is going to be falling off as 1 over r squared. And that's what's shown over here. Radially, the density is falling off as 1 over r squared. And that is true for any radial direction, including radial directions through the CIR. Again, any portion of the CIR is, again, just a different speeds of solar wind that are radially expanding. And therefore, these regions of the CIR are also falling off as 1 over r squared. What we're, of course, interested in is not the density along any particular radial direction. What we're interested in is the density along this line of sight. So if we take the density, the radial expanding 1 over r squared density, and look at how that varies along the line of sight, then what we end up with is this expression over here. The density along the line of sight goes as the sine squared of the psi angle. And you can see a plot of that right over here. So this is the density along the entire line of sight from the observer's position all the way out to infinity at 180 degrees. Okay, that's what I thought. So what we're interested in is the density only within the CIR. So what we're going to assume is that within this, everything outside of the CIR, we're going to assume perfect background subtraction. That's what the SOC is going to do for us, right? Perfect background subtraction. And we're only going to have the CIR left within the image. And so looking at only the density within the CIR, what we're then interested in is this pink portion of the density along the line of sight. And basically, that's the same expression as we had before, the sine squared psi multiplied by a boxcar function, which is 0 everywhere outside the area of interest, and then 1 within the area of interest. The boxcar function is centered on this angle capital psi c, and it has a half width of delta psi, so plus minus delta psi with respect to the central angle. So that's the density expression we're going to now substitute into our expression from a few slides back. And then when you substitute in, this is the expression for the polarization ratio that falls out. It's an expression that involves two characteristics of the CIR. The polarization ratio responds to changes in location, psi c, and changes in the width of the CIR along a particular line of sight. The same thing, by the way, is true also for CMEs, that the polarization ratio depends on what the line is or where the CME is located, and also how broad the CME is, where the mass, how broad the region where mass is located is. So here is our expression for the polarization ratio for an ideal CIR. So here's how this a plot of how this polarization ratio varies. This is a plot showing the polarization ratio as a function of the feature half width, where each of these different lines are fixed values of the central angle. So here in this dark blue, we have the polarization ratio as it varies for different half widths along the Thomson sphere. If the CIR or the solar wind feature is centered on the Thomson sphere, then as the width of the feature increases, you have more material far from the Thomson sphere, and therefore the polarization increases. The polarization goes up from 0 to some higher level. If you have a location that is very, very far, if the solar wind feature is already very far from the Thomson sphere, then you start off with a high polarization ratio, but as you increase the width, then you end up having more material coming closer to the Thomson sphere, and therefore the polarization ratio starts dropping. This is a similar plot again, except instead of having, now we have polarization ratio versus feature angle, the central angle of the feature, for different values of fixed values of the width of the CI of the feature. So different fixed to each line, each colored line corresponds to a different fixed width. Particularly interesting is this dark blue feature, or dark blue line over here, which is a asymptotic limit of as the width of the solar wind feature approaches 0 degrees. So it's basically a small feature limit or a point limit. And when that happens, then the polarization ratio simplifies from this expression down to a much simpler expression here, just co-squared of the feature angle. So this is actually a situation that we're interested in, since a priori we don't know where the CIR is located. We don't know how broad the CIR is. So if we can get rid of one of these parameters, then we can use the polarization ratio, the measured polarization ratio, to obtain quantitative information on where the CIR is located. So this is something that we're really interested in, and I'm going to call this, as I have in previous papers, the superparticle construction. Now you may be thinking, well, is this a good idea? After all, what I'm suggesting is that we're going to take all the material that is within this line of sight, all the material within this compressed region, within this line of sight, and I'm going to shove it all into one point. Is that a smart idea? Is that a clever idea, or is that an absurd idea? So what we're going to do is we're going to look at a few sample calculations, choosing values of the feature central feature position psi c and its width delta psi, calculate what the polarization ratio is using this formula over here, and then apply the superparticle construction, which says that the position of the point is related to the polarization ratio over here, and then we're going to compare our superparticle position to the ground truth position and see how well we do. Now, what's actually interesting, and I'm just going to skip to this slide, what's actually, or let me go back for 1 second over here. One important point is that for a CIR, the positions of interest that we are most interested in, most of the CIR is always going to be, especially the compression region of the CIR, is going to be lying behind the Thomson sphere. So when I'm looking at where, at the error in our calculation, what I'm interested in is positions that are behind the Thomson sphere, so central feature angles that are greater than 90 degrees. And what's interesting is that as long as the width of the CIR, the half width of the CIR, isn't too large, 15 degrees maybe, certainly not much more than 35 degrees, then collapsing the whole of the CIR down to a single point doesn't seem to introduce a whole lot more than 5, maybe 10, up to 15% error. So in fact, collapsing a large feature down to a point does not introduce a whole lot of error and makes this technique usable and producing results that are meaningful. Now, there is one big but. Yes, there is one big but, and that is I have been assuming that the line of sight is passing through only a single feature. So when you're passing through only a single feature, then it makes sense to use the superparticle construction and come out with a single number defining where that feature is. But if you have a fragmented solar wind where you have numerous features that you're looking through, and you don't know where any of these features are beforehand, and you don't know what the size of the features are beforehand, then assigning a single value from the superparticle construction to, I'm not sure what you're assigning to what over here. So really, it is important to, when you're using a superparticle construction, that you want to do it for a simple background or for a simple solar wind. Thank you.
Thank you. All right, we're going to move on to the next one, which is Maher Dea. So Maher's going to be talking about shocks.
Okay, thank you. Okay, good morning, everyone. So I won't be showing all these nice simulations over the last 2 days that people have been showing, but we're going to move from the remote sensing regime into the in situ ground truth stuff. And I'm going to show you a proof of concept of how we connect the PUNCH observations into advancing space weather forecasting. So what I'm going to present now, the paper just got out. And I will show that at the very last slide. I'm presenting how to forecast the shock-associated ESPs, which are the energetic storm particle intensities in the inner heliosphere. And this is a proof of concept for PUNCH. So when we have observations, then we can see how good this thing works. First, what are ESPs? What you see here, the cartoon on the left side, is basically just a coronal mass ejection leaving the sun and plowing in the interplanetary space. On the right side, do you have a laser pointer?
No.
Or a mouse? Okay.
Here's a mouse, and you put it on here. It will show up there.
Okay, good. So what you see here, thank you. What you see here on the left is the cartoon of a coronal mass ejection leaving the sun and plowing in the interplanetary space. This is the ejecta of the CME, and if the CME is fast enough, it can often drive an interplanetary shock. This shock accelerates particles along the way, and we observe it at 1 AU and after. The particle accelerated are often trapped in the acceleration region of the shock. So from the in situ perspective, now we look at the right panel. The top panel is just the X-ray flare observations from GOES. The bottom panel is the particle data. And you can see this is a nice isolated SEP event. So when the event starts very early at the sun, all these SEPs come in very fast. And then it takes about 2 days for the CME to arrive to the spacecraft. This is the plasma signature of the CME here, very clear. And when the shock arrives, it brings this little tiny peak. This tiny peak of particle enhancement is the ESP component. And this ESP component sometimes several orders of magnitude. So it really dumps a very large amount of particles into the in situ sensors. These ESPs have different shapes and forms. So if you look at the statistics of the data that we have, it's not always the same shape. It has really different shapes and forms, further highlighting that we still do not fully understand how these particles escape from the shock trapping region or how they are even accelerated as the shock is propagating in the interplanetary space. Why these are important? These are important for two main reasons. The first reason is that it would enhance our understanding of the shock acceleration itself. For instance, do we have these small variability at the shock front and from the perspective of magnetic connectivity as well? So understanding ESPs more would directly refer to how they are accelerated at the propagating shock. And then the second part, which is more important, is that the space weather aspect of this. Now, with the advancement and the need of the space weather forecasting, understanding SEPs and forecasting them is very important. You hear a lot about forecasting SEPs, but ESPs are this very special component in SEPs that affects the peak fluxes. When we hear about the peak fluxes, it's very important. And they are large enough. For instance, here I'm just showing an example where sometimes they are large enough that they saturate the instruments that we have. This is for the same event. The bottom panel is from an SSD-based instrument, so you don't see the saturation. But the top one is the time of flight, and you can see pretty much the high voltage cannot keep up. And then you have all these saturated fluxes in here. So what are the forecasting efforts that have been done so far for ESPs? Not much, partly because we lack the low energy aspect of the observations. The most prominent ones are basically looking at particles escaping from the shock. So right before your shock arrives into the spacecraft, you see variability in the suprathermal component in there. You see that the energy distribution and the density of particles are varying. So there are several studies out there that they try to utilize this observation to understand the arriving shock component, maybe leading with leading time from 12 to 24 hours, but the probability or the accuracy of the forecasting is not that much. And there are more ongoing work. I'll skip this slide. Still very ongoing. The other approach of understanding this is that you have a very large set of these ESPs, and then you basically look at all the properties and do a multivariate study and see, the whole full matrix of correlations and trying to understand why quantity A is related to quantity B and how it's related. You will find quantities are related, but it's all vague because the variability of event to event is so large in ESPs that it's really hard to close on something. So the objective of the study here, now we are at PUNCH, and we are relating PUNCH to all these in situ observations. PUNCH will not see things in situ. It would image the CMEs or CIRs. I'm bringing CIRs here because also CIRs, sometimes they develop shocks as well within one AU, and we observe that. But the main focus would be on ESPs because these shocks are stronger and much more pronounced. So the goal here is to basically use what PUNCH is going to observe from the propagating shock with respect to the solar wind in the background and try to infer information about the ESP component, about the particle component. And it's a very simple study, and the result is very clear as well. So what we did is that we went and we looked at a very long catalog of ESP events, and we did a selection criteria where the ESP should be associated with a particle enhancement, because as I showed earlier, some ESPs do not show that. So we pick the events where we have an enhancement in the ESP component, and then we pick a certain window around the event, and we just look at the peak flux of this one. We do the same for CIRs as well. We end up with, where's the number? 59 events for, I cannot see. Okay, I believe it's 59 for ESPs and 74 for CIRs. And what you see on the left panel here, this is the ICME situation you see the particle component here, and the speed signature, the solar wind speed signature, you see the jump of the solar wind speed. And we have the same in the case of CIRs at the associated shock as well. It's not much, but for ASPs, it's well pronounced. And we take all our events, we take the delta V, and we take the peak intensities. The peak intensities was integrated over a certain range of energies, up to few MeVs. And you look at the correlation now between the peak intensity and the peak flux, for instance, the speed of the solar wind or the delta V. So we exploit all these correlations, and we see that the nicest correlation comes in delta V. So the speed jump is very much related to the peak intensity. And we just do simple regression here, and we got the relation between the delta V and the peak intensities. Now we go to the punch stuff. Now this is the magic that Raphael was showing yesterday with the ball tracking things. Okay, so Raphael has this algorithm that can track structures in the solar wind, and it tells you the speed at every instant in time and space, I believe. So tracking these structures now, we can tell the speed of the background and then the speed of the structure that's going on top of that. So we should be able to eventually infer delta V. We have the relation that links the peak intensities with delta V. Once we have the first measurement of this delta V, we can have an estimate of the fluxes that are we going to observe when the ESP component passes by 1 AU or different locations in the inner heliosphere as well. Now, the good thing about this one is that it's a continuous forecasting. So you would observe it, you would issue some forecast for the peak intensity. Once you have an updated speed value, because the speed is going to change as well. So delta V is not going to be fixed as a function of time. So once delta V is changing, we have also updated forecast all the time going on. And so we kind of developed a simple potential algorithm of this forecasting, pretty much summarizing what I was saying now, where we have a continuous forecasting of these structures at 1 AU. We put this in the punch collection, and the paper is out. Of course, there are some caveats, but I think this really all awaits the punch data. Once the punch data is in, then we will do a good study on this one. Do I still have time? Okay, and I want to show you something. It's punchy and not punchy. So it's not really punch, but I really got the idea completely from punch, from an observation I had with Dan Seaton, I don't know if he's around, and Craig as well at the Space Weather Workshop a couple of years ago. We were standing outside and discussing how they get these very nice coronal images they have and the background subtraction they apply. And then I was thinking of this one. So what they do is, if I'm understanding things correctly, they take these very nice images and they look at the minimum pixel in every frame with a very large set of frames, and they consider that as a stationary background. And then they subtract this stationary background and they can detect fast variations. That's why they have these very nice movies. Of course, they do maybe more things, but this is at least one of the basic techniques that they do. So I took that and I wanted to apply it to something very different, the IBEX data. So IBEX is Punch's older sister, basically. It's a SMACS mission as well. And with the goal to observe energetic neutral atoms from the interstellar interface. That's the heliospheric boundary. So it's basically, you have charge exchange between the solar wind at the boundaries of our solar system with the colder interstellar neutrals. And then you create ENAs. At the right pitch angle, the ENA would come back to 1 AU. IBEX is orbiting Earth. And then you can observe that over a certain length of time. You can construct heliospheric maps. You probably have seen some of these. These are different maps for different energies and different times. This is worth one solar cycle, but I averaged every 2-3 years at the same time. And the main thing that stands out is the background that the ENAs are coming from all directions. And there's this structure in the sky that they call it ribbon. This ribbon structure appears mostly at solar wind speeds. This is like 1.1 keV. And you can see there are temporal variations and spatial variations and different intensities. The point is not here. So then I take this data and there was a picture. Okay, I think it's not updated. Okay. So then I take this data, I take each map of these, and then I look at the minimum pixel and time and energy as well. And I construct the minimum maps, something similar to what they do with the coronal maps. So in this one, these are the minimum maps. They look like real data maps, but each pixel is coming from a different time, from a different map. And these indices of these pixels is on the right side. And then I take the original data and I subtract it from the minimum maps. I want to see if I can detect these fast variations, and just something really pops out so quick. It literally took half an hour to do all this. And it's exactly what I was looking for. What I was looking for is if I can see the fast solar wind input at the high latitudes, and it shows here, and then it shows here. You can see the fast solar wind variations. These ENAs are created at higher energies, at high latitudes, because of the injection of the fast solar wind going from the pole, going all the way to the outer boundaries. And then at this energy, you can see this structure here in the middle. This is the pressure pulse. So we had a pressure pulse in 2014 in the solar wind dynamic pressure. And this pressure pulse showed up about 2 to 3 years, because it takes time for the solar wind to go back, charge exchange, and come back to you. So this pressure pulse appeared in the ENA data a few years after. But if you do this technique, it also shows up that the most two structures that really vary in the sky is the high latitude solar wind and the pressure pulse we observe. And you can see it even at slightly lower energies here, because this is what they call the knot. It's the region where basically the solar wind is injected. So that's why you see it brightening first. And then you can see these two changes. This is still ongoing work, but I wanted to present it here just to give a proper credit to PUNCH, because it really came out of the discussions that are PUNCH related. So thank you.
All right, thank you. And next, we have a talk by Nathaniel Laurent, who is going to be talking about 3D CME trajectories validation. Go ahead, Nathaniel.
Hello, everyone. So I'm an intern at SWRI, and today I'm going to be showing some of my work from the past few months on determining positioning of CME. So sort of a combination of what Kurt showed and what Elena showed. So we use the CME challenge dataset. Okay, so you've heard a lot about this already, but we use Thomson scattering to determine the position of a CME through the polarization ratio. So that's the equation that you see down here. And one consequence of using this method for determining positions is there is a discrepancy between a ghost trajectory and a true trajectory that results from the plus or minus there in that equation. And that is plotted on the upper right, where one of those trajectories will be radial, and that's the true trajectory of the CME, and then the other one is a ghost trajectory. So a big part of this is determining, distinguishing between those two. Okay, so this was sort of performed as a single blind study with the PUNCH CME challenge data. So we did our calculations, performed our model on the both the set of polarized brightness and total brightness images that were disseminated to the public, and then compared these in the end to the set of ground truth data. And so our methodology involves selecting points on the edge of the CME front for each time step for the multiple CMEs and their different perspectives, performing the analytic inversion using the PBB ratio to determine an out-of-plane exit angle. And something we'll find that is very important is both background subtracting this data and then performing a post-processing perspective correction. Part of this is the analytic inversion. So that's what Kurt was talking about earlier. We use the polarization ratio from each pixel in the along the trajectory of the CME. And initially implemented, this really doesn't give us much, The blue dashed and orange dashed lines in the figure on the upper right show that we don't get a very radial trajectory and can't distinguish between the ghost and real trajectories. And the cause of this is the unpolarized F corona and polarized K corona, which distort the PBB ratio and prevent us from getting good data. And the what shows that is the elongation angle explains the variation in the positive and negative square root calculations. So the polarization ratio remains mostly constant along the path of the CME. So to combat this, we implement a background subtraction method. And since the time series of the CME challenge dataset is not long enough to establish a reliable long-term baseline, we used a method that uses a single image, and we sample along a radial line passing through the selected point on the CME front, and then fit a function to that data. So you see that on the lower right here. The fit curve is in orange and the original data is in blue. And so we do model that background, and the excess brightness in the original data in that blue curve is the CME. And that red point is the selected point on the front. And so we do this for each image, and the the function that we use to model the background is the one shown there, where A models the overall brightness of a radially stratified corona, P models that degree of stratification, and B models the effects of a constant brightness background. So implementing this background subtraction method, we see on the left the dotted lines are before the correction and the dashed lines are after. And already that orange dashed line seems to be much more radial, and indicating that that is the real trajectory of the CME, and then the ghost trajectory is that dashed blue line. And the direct effects of the background subtraction method are shown on the right here, where we can see that the CME is much more isolated from the background, and then those black pixels are truncated due to the background being slightly brighter directly behind the CME. And this overall causes a shift towards the Thomson surface due to the change in polarization ratio. Additionally, we also have to account for the discrepancy between the furthest point on the CME front versus the point observed on the CME front along the line of sight. So on the upper right, the point along the line of sight is offset by angle theta, centered at the center of the CME from the actual furthest point from the sun center. And we use the equations there to account for that discrepancy. This involves modeling the CME as a sphere currently. We assume that the curvature along the scattering plane is the same as the curvature along the sky plane. And that is done by manually selecting a bounding circle for the CME at each time step to find that curvature and account for the change in perspective. So this perspective correction results are shown on the right here for that same CME we've been looking at this entire time. We can see that the orange solid and the blue solid lines are after the perspective correction. And again, even more so now, the orange line seems to be the actual trajectory of the CME, and the blue line is not radial. So that would be the ghost trajectory. And the orange line does deviate near the end, and that is due to the background subtraction method and the fact that the CME is optically thin. Okay, and so finally we compare with the ground truth. So the purple lines here, both on the left and right, are from two different perspectives of the same CME. And so this is the ground truth simulation parameter data that we see. So the solid blue lines, the solid blue line on the left matches the path of the CME very well. And then similarly on the right, the orange line matches that CME. So whether the CME is inside or outside the Thomson surface, we can effectively model it. And this was applied to multiple CMEs in the CME challenge data set. Another way we can measure the effectiveness of the model is by finding exactly how well we are background subtracting the data. After I reached out to Anna, she generated a perfectly subtracted background. So just removing the rest of the corona from the CME images, sort of a way to compare our background subtraction to. So we performed the same calculations on that set of data on each of those selected points on the CME front, and then compared the output calculations for each. And so this can serve as a sort of baseline for the background subtraction model. So on the figures on the right, we see the green and red curves are the positive and negative square root calculations for the perfectly subtracted data, and then the orange and blue are for the normally subtracted data. And those work phenomenally at the early time steps. So we subtract the background well, and then the data does degrade somewhat near the end due to the lower signal to noise ratio as the CME moves further from the sun. Okay, and so in summary, we have demonstrated that with the CME challenge data that we can use time series observations of the polarization ratio on the CME front to distinguish between ghost and real CME trajectories, resulting from the methodology for determining an out-of-plane exit angle. And by fitting an analytic function to the background of a CME, we can isolate it through background subtraction, and through modeling the surface of the CME, we can analytically correct for perspective effects. Some current limitations of this method is that we've tested on fairly few CMEs. The CME challenge dataset contains 4 CMEs, each with a few perspectives each. And of course, we have only performed those calculations on simulated data so far. So we would love to implement on actual punch flight data, and additionally implement automated front-end curvature detection. So modeling the CME so we don't have to use hand-selected CME front and boundary points. So thank you, and go punch.
All right, thank you. Very cool stuff. All right, so our final talk of this session is David Barnes, who's going to be talking us about more synthetic CMEs.
Hi, I hope you can hear me. My name's David Barnes. I'm from RAL Space in the UK. I'm going to be talking to you about some work that we've been doing as part of an ISI team that I'm co-leading, where we're using synthetic images, synthetic white light images, in order to perform inverse modeling, or specifically tomography, in order to build up 3D maps of coronal mass ejection density. So coronal mass ejections are typically observed in white light using coronagraphs or wide angle images, such as these images here. The limitation of this is that CME parameters are always loosely constrained. And so typically we apply forward models, things like GCS, in order to build up an idea of CME morphology, direction, etc. But forward modeling can only give you limited information. It can never tell you anything about CME internal structure or density structure or mass, for example. And so an alternative method is inverse modeling or tomography, where you use multiple vantage points in order to constrain the 3D distribution. So this method hasn't enjoyed much success when applied to CMEs so far, because typically you need a lot of vantage points, so a lot of different observing spacecraft, probably more than 3. And so that's why we decided to do this with simulations. If we simulate images, then we can have as many spacecraft as we want. So we can perform this method and see how well it works using different combination of spacecraft. And so in the method we've used basically is to perform MHD simulations use those simulations to create synthetic images, and then use those synthetic images to perform the tomography. So we proposed this as an ISI team. It was accepted in 2023. We had our first and second meeting so far, and we've got our final meeting coming up in a couple of months. So we've made quite a lot of progress with this, and I'll try and show you some of the results that we've got so far. So first of all, I should explain what I mean when I say tomography. Tomography is a word that's used to describe a very broad range of methods. So specifically here, I'm talking about discrete tomography. What we do is we take the heliosphere, we divide it into a three-dimensional grid. As Kurt explained quite thoroughly earlier, Thompson scattering is dependent on an integral along your line of sight. And so the density distribution along your line of sight determines what you see in an image pixel. By dividing the heliosphere into a 3D grid, you can approximate that integral as a sum of finite elements, where each element is a contribution from an individual grid cell. So if you take a coronagraph image or a sequence of images from different spacecraft, then you can do that for every image pixel, and you can build up an inverse equation. So I'll see if you can see the mouse there. So yeah, we can build up an inverse equation that approximates the line of sight integral in every image pixel as a function of the unknown density over the grid. And then we can solve that to get a map of the 3D density. So this equation, Y is just an array containing all the image pixels. X is an array containing the unknown density over the grid. And H is a matrix that contains the physics of Thompson scattering, including polarization. And so we know Y, we know we can calculate H. And so we use that to solve this inverse equation to give us a density. Okay, so I'll describe the simulations quickly. We're using the magnetic algorithm outside the sphere code, which is developed by the guys at PSI. And so this is an MHD simulation that constructs the coronal magnetic field and can simulate background solar wind and CME propagation. So I'll just show that again. It operates in two domains. On the bottom, you can see the corona, which goes out to about 30 solar radii, and at the top you can see the heliospheric domain, which goes out to just beyond 1 AU. And so we use this to perform simulations for 3 different CMEs. We're looking at a slower CME, a faster one, and a very fast one. And these are based on real events that are from 2021, 2020, and 2017. So once we perform those simulations, we have a 3D density distribution. We can put our synthetic spacecraft into the model. So what we do is we came up with sort of what we consider plausible fleets of spacecraft. So for example, on the left here, we have a spacecraft at L1, L4, L5, and a 4th spacecraft above the ecliptic. The other configuration is a ring of spacecraft in the ecliptic, so a 6 spacecraft ring. In fact, in these configurations, R1 and L1 are at the same place. So effectively, we have 9 observing spacecraft. And from those 9 possible spacecraft, we choose different combinations. So we've gone with 5 different combinations, 3 spacecraft, L1, L4, L5, 3 spacecraft in a ring. And then we've got this configuration here of 4 spacecraft. We've got a configuration of 6. And finally, we've got a configuration of 7 spacecraft, which is this ring with an extra observer outside the ecliptic. Okay, so what do these simulated images look like? So this shows an example of a CME erupting as observed from L1, L4, and L5. These are different images. I'll just show that again. So yeah, from those I construct, I do some basic processing to construct images from each of the 9 spacecraft. So I've occulted anything within 4 solar radii because we're not really interested in what's happening near the sun. I've also reduced the resolution because this inverse equation I've described is huge. There's no way we could do it with full resolution images. And so, yeah, I reduced the resolution to about 128 by 128 pixels. I've given this talk before and people always say that's a bit low maybe, but I think the point is that we're doing loads of simulations. We're looking at 3 CMEs, 5 different combinations of spacecraft. We're looking at a sequence of images. I had to run this code hundreds of times, so I chose that. so we can still look at large scale structure. We're not going to see any small scale structure in this, but I think that's good enough to sort of demonstrate the method. Okay, and quickly I'll just show polarization. We've discussed this. This has been discussed in previous talks. Obviously, you can look at total brightness, polarized brightness, and then take the ratio of the two to give you the degree of polarization, which is what's shown on the right. And this shows very well how much more information you get about the 3D structure of CMEs from looking at polarized brightness images. So that's an example from L4 and L5. Okay, so how well does this work at reconstructing the densities? So hopefully you can see that animation. So on the right is the original mass simulation for the second CME that we've simulated. So I've subtracted low density values just to reveal the 3D structure of the CME. So that was the original CME that's used to create the synthetic images. And then we've reconstructed that density using tomography applied to different combinations of spacecraft. So top left, you can see the result we get from 3 spacecraft. It's actually not bad. Using just 3 spacecraft, you can see there's definitely some structure there, although we don't resolve the full 3D structure of the CME very well. If we increase to 4 spacecraft, then we get a much better reconstruction already. And then if you increase the number further to 6 or 7 spacecraft, you can get pretty close to what the actual 3D structure of the CME is. So this just shows the same results, but on the left, the solution is created using total brightness images. On the right, we also include polarized brightness. And as the GIF steps through, you can see the number of spacecraft changes. And what's important about this is it shows you how you get a better result using polarized brightness. But as the number of spacecraft increases, then that advantage you get from polarized brightness becomes less significant, which is interesting. I think this slide shows the same thing differently. So it's basically, yeah, different number of spacecraft in each panel are switching between polarized and unpolarized solution. And so basically what that tells us is polarization is good. This is an ISI project. It's not a mission proposal, so we're not expecting anyone to launch 6 or 7 spacecraft. And so it's important to, I think, to conclude from this that actually you can do this kind of analysis using only a few spacecraft if you had polarized brightness measurements. So I think that's really interesting. I'm running out of time, so fortunately I've nearly reached the end. Basically, what this slide shows is because we're doing simulations, we know what the original density is, so we can compare our reconstructed density as a means to quantify how well the tomography method works. So basically, we just look at the difference between the density in every grid cell compared between the solution and the original. And so basically, yeah, the same conclusions as I said before. Increasing the number of spacecraft improves the result massively. Having polarized brightness measurements helps a lot, although that advantage you get from polarization diminishes as the number of spacecraft increases. So I've gone over 10 minutes, so I should probably leave it there. So I'll just leave you with my summary slide. So thanks very much.
We need the lavaliers. All right, thank you, everybody. Now, can we have all of the speakers from this morning come up to the table?